Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. In the quiet, damp corners of the world's forests, hidden under the decay of fallen logs and leaf litter, lives one of the most unlikely geniuses on the planet. It isn't a bird, a mammal, or even an insect. It is a single-celled organism known as Physarum polycephalum, commonly referred to as the slime mold. At first glance, it looks like nothing more than a splash of vibrant yellow paint or a strange fungal growth on a rotten stump. But beneath its simplistic, gooey exterior lies an architectural mastermind that is currently revolutionizing how human beings think about logistics, urban planning, and even the future of artificial intelligence. For decades, we believed that complex problem-solving required a brain, a centralized hub of neurons capable of processing data and making decisions. The slime mold, however, has no brain, no nervous system, and not a single neuron to its name. Yet, it can solve the traveling salesman problem, navigate complex mazes, and design transit networks that rival those built by our top engineers. The most famous example of this occurred in 2010 when researchers in Japan and the United Kingdom decided to put the slime mold to the ultimate test. They placed oat flakes on a surface in a pattern that mirrored the layout of Tokyo and its surrounding 36 cities. Oat flakes are a favorite snack for the slime mold, so it began to grow. Initially, the organism spread out in a thin, uniform sheet, exploring the space in all directions. However, as it encountered the oat flakes, it began to refine its shape. It strengthened the connections between the food sources and retracted from areas where there was no food. Within 26 hours, the slime mold had constructed a network of nutrient-carrying tubes that was nearly identical to the actual Tokyo rail system. More impressively, the slime mold's version was actually more efficient and resilient to breakage than the human-designed one. It had perfectly balanced the need for short paths with the need for redundancy, ensuring that if one path was damaged, the rest of the network could still function. How does a single cell achieve such a feat? The secret lies in a biological process called shuttle streaming. The slime mold is essentially a giant bag of protoplasm that pulses every 60 to 90 seconds. These rhythmic contractions push fluid back and forth throughout the organism. When a part of the slime mold finds something beneficial, like food or moisture, it pulses faster, widening the tubes in that direction. When it encounters something harmful, like bright light or dry air, the pulses slow down and the tubes shrink. This creates a decentralized feedback loop where every part of the cell communicates with every other part through the physics of fluid pressure. It is a living, breathing algorithm that optimizes itself in real time without any central command. Perhaps even more startling is the discovery that slime molds possess a form of spatial memory. As the organism moves, it leaves behind a trail of translucent extracellular slime. This isn't just waste, it's a physical record of where the organism has already been. When the slime mold encounters its own previous trails, it knows to turn away, preventing it from wasting energy searching the same spot twice. This externalized memory allows a brainless cell to remember its past and plan its future movements with mathematical precision. This biological wisdom is now being harvested by human engineers. Researchers are using slime mold algorithms to design more efficient fiber optic networks and data routing protocols for the internet. Because the slime mold is naturally programmed to find the shortest path while avoiding obstacles, its logic is being applied to fire evacuation simulations in large buildings, helping us understand how crowds can move most efficiently during emergencies. In the world of electronics, researchers are looking at the slime mold to help design the next generation of microchips. As circuits become smaller and more complex, the organic, self-organizing patterns of the slime mold offer a blueprint for layouts that are far more efficient than anything a human could manually draft. The slime mold architect challenges our very definition of intelligence. It suggests that logic isn't just a product of gray matter, but a fundamental property of life and physics. By studying these ancient organisms, we are learning that sometimes the best way to solve a global logistics crisis is to stop overthinking and start flowing. We are finding that nature, through millions of years of evolution, has already written the code for the most efficient systems imaginable. All we have to do is learn how to read it. For more incredible facts like this, don't forget to subscribe and turn on notifications.